As we continue our exploration of the slope of a curve at a point, let's now use an arbitrary value for the point as opposed to an actual value of x. So the slope of the curve y equals f of x at the point a comma f of a is the number represented by the limit as h approaches 0 of f of a plus h minus f of a all over h. Remember, our denominator was already simplifying to h, so let's just start that way. Let's let function h be 1 over x. Let's do two things. Find the slope of the curve at x equal a, and then where does that slope actually equal negative 1/4? So for part A, we are going to want to take the limit as h approaches 0 of 1 over a plus h minus 1 over a all over h. And for us to calculate this, we need to simplify it in such a way so that that factor of h in the denominator is removed from the fraction. So before we actually consider the limit, let's explore the fraction and see if we can write it another way. By doing this, this will allow us to avoid having to write limit as we do all this algebraic work. Well, first thing I'm going to do is I'm going to multiply by the number 1. The name for the number 1 I'm going to use is the result of the common denominator of all the fractions. So in this case, a times a plus h over a times a plus h. And when we perform this multiplication, a times a plus h multiplied by 1 over a plus h, the a plus h factors are going to reduce, and we're just going to be left with a. When we take a times a plus h times 1 over a, the a factors are going to reduce to 1, and we're going to be left with a plus h. The key thing here is it's a subtract, so we have to make sure we subtract the a plus h. And then the denominator, our multiplication, is going to be h times a plus h. Our numerator is going to simplify down to negative h, and our denominator is h times a plus h. The two factors of h will reduce, and so this fraction is negative 1 times a plus h. And that's the fraction we're going to want to look at the limit of. So the limit is h approaches 0 of negative 1 over a times a plus h. Remember, the limit of a constant is itself, so the limit of negative 1 is negative 1. And in our denominator, a is going to stay h, and a plus h is going to approach a as a gets closer to 0. So we have a times a, or a squared. This would be the slope of the tangent, or the slope of the curve, anywhere along the curve. So when a is 3, we get negative 1/3. When a is 5, we get negative 1/25. So the power in this is the fact that we're using an arbitrary point, and that gives us a general answer that we can use for individual values of x. So in part B here, let's extend the page a little bit. In part B, we wanted to know when the slope was negative 1/4. So we're going to set negative 1 over a squared equal to, double check here, it was negative 1/4. So when we do cross products, we get negative a squared equals, let's see, negative 4. A squared equals positive 4. A equals plus or minus 2. So at the point 2 comma 1/2, we have a slope of negative 1/4. And at the point negative 2 comma 1/2, we have a slope, or that would be negative 1/2. We have a slope of negative 1/4. Recall here that the graph of 1 over x looks like this. It's the reciprocal function. And so here at 2, the slope of the tangent is negative 1/4. And here at negative 2, the slope of the tangent is negative 1/4 as well. Revisiting speed, if y equals f of x is a position function for an object, it describes the position of the object at any point in time, then the average speed would be equal to the average rate of change of its position over time. This is traditionally what we call the slope between 2 points, or the secant slope. Its instantaneous speed at any time t is the instantaneous rate of change of position with respect to time. It's that limit that we've been looking at. So the limit as h approaches 0 of f of t plus h minus f of t over h. Later, instead of using the word instantaneous rate of change all the time, we're going to tend to just call it rate of change. So that will always mean instantaneous rate of change. For average rate of change, we'll say average rate of change. So in our example, the free fall on Mars is 1.86 t squared meters with t in seconds. Assume a rock is dropped from a height of 200-meter cliff. Find the speed of the rock at t equal 1 second. Well, on this particular problem, our function for its height at any time is going to be 200 minus 1.86 t squared. And so the limit that we're going to need to look at is the limit as h approaches 0 of h of t plus a h minus h of t over h. Okay, I apologize for naming the function h in addition to having a term that's an h as well. So let's drop down a little bit here. And let's plug in and simplify the fraction before we go back and look at the limit. So h of t plus h is going to be 200 minus 1.86 t plus h squared. Then h of t is 200 minus 1.86 t squared. That's all going to be over h. As we simplify the numerator, we have 200. We square this. The square is going to be t squared plus 2th plus h squared. All that's multiplied by negative 1.86. So that's going to give us negative 1.86 t squared minus 3.72, I think, th minus 1.86 t squared. Distribute the minus through here. Gives us a minus 200 plus 1.86 t squared. All that's over h. Now looking through here, we have 200 minus 200 makes 0. And a negative 1.86 t squared and a positive 1.86 t squared makes 0. So we're left with this expression in the center. And there's something wrong here. This last term should be an h squared. All right. If we look at the two terms that are left in the numerator, they have a common factor of negative 1.86h. That would leave us here with a 2. And back here it would leave us with a what? Minus h. And that would leave us with a 2t in there, actually. We have the t factor. This is all over h. So the h factors will reduce in our expression. Let's just multiply that back out. Oh, no, let's keep it as it is. 0.86 times 2t minus h. Let's go back up to where we had our limit. Right here. And so now we're really looking at the limit as h approaches 0 of negative 1.86 times 2t minus h. And negative 1.86 times 2t minus h. The limit of that, the limit of negative 1.86 is not going to change because it doesn't have a h. This part, 2t minus h, is going to approach whatever 2t is. And so if I multiply that back out, I get that my limit is equal to negative 3.72 times t. In our particular problem, put the 1 back in. We get the speed at negative 3.72 meters per second. Now you might be asking, why not at the very start, instead of doing h of t plus h, why don't we do h of 1 plus h? It's true that that would give us the answer for this particular problem and avoid having to work with so many variables, but when we use the t plus h, that allows us to get to an expression that represents the speed at any time t, the instantaneous rate of change. All we need to do is to plug in the time for t, like we plugged in t equals 1. Right now we can calculate the speed of that rock after 3 seconds by plugging in 3 and take negative 3.72 times 3, and that would tell us the speed of the rock. So oftentimes, especially when we're going to be using or calculating speed at a lot of different times, using the general form here is much better than using the specific or particular form. And just to close, all of these things are saying the same thing. When it says the slope of y equals f of x at x equals a, talking about the slope of a curve, that means the same as the slope of the tangent to y equals f of x at x equals a. That's the same thing as the rate of change. Remember, that's the instantaneous rate of change of f of x with respect to x at x equals a. And the limit of f of a plus h minus f of a over h as h approaches 0. Those four things are interchangeable. When you hear one, it also means the other. So if you need to find the slope of the tangent line, that's saying you need to find the slope of the curve, which is meaning you could use this particular algebraic expression to calculate that. Now, this particular limit that we see in number 4 is one of the two most important mathematical objects that we have in calculus. And in the next chapter, we're going to go into a more detailed, thorough study of it.